Hello, and welcome to this lecture on hydrological cycle. My name is Nikhil Kumar. I'm a postdoctoral scholar at the Department of Land, Air, and Water Resources at University of California, Davis. So here is an overview of the key topics that we will cover today. So we'll start off with the hydrological cycle and then global water resources. Then we'll talk about water balance equation, residence time, and finally we'll talk about drainage basin. So first, what is hydrology? So, hydrology is the science of water. It tries to understand how water moves over and through the earth. So, we can say it is the science of occurrence, distribution, and movement of water in all its forms on, above, and under the earth's surface. Hydrology is fascinating and essential. All life on earth depends on water, and there are critical scientific questions that demand our attention. For example, how much water there is available for development and feeding hungry mouths and for a healthy environment. How can we better protect ourselves from water threats such as floods and droughts? How do human activities influence hydrological systems? What impact does climate change will have on hydrological systems? So let's talk about the water cycle, which we are all familiar with. So I will start with the process of evaporation. So evaporation can occur from the surface of the ocean, in this river, or this lake. So at any given moment, there is going to be water evaporating off that surface. So water molecules that were in their liquid state, they just have enough energy to bounce away and go into gas state. So, and the water in gas state is water vapor. So this water vapor is going to rise with the hot air, and as it rises and the overall temperature cools down, these water vapor condense into little droplets. So it will condense around little microscopic dust particles to form these water droplets, which won't be visible from a naked eye. And if it is cold enough, then this might also form ice crystals, and that's what clouds basically are. So if you go outside on a cloudy day, you might see the clouds are moving along with the wind. That's the process of transportation, which is moving the droplets within these clouds also along with the wind. So once these droplets they get heavy enough, they precipitate down. They could precipitate back to the ocean, or you can go onto the top of this mountain and they can precipitate back here. And if the air is cold enough and you have the right conditions, the precipitation might be snow here. And eventually, when the conditions here warm up, if they do, the snow would melt and would result into runoff. But for the areas that aren't cold enough to snow, the precipitation might fall as rain. And this rainwater often infiltrate into the soil and percolate deeper into the groundwater. So if you look around and you'll see that all these rivers and these lakes, so there is a lot of water out there. But it turns out that around one third of the Earth's fresh water is actually stored in these groundwater aquifers. So in generally, the rivers that are formed from the surface runoff or the snow melt runoff. And if you see the rivers near your home filling up after the rainfall, it means that groundwater has become saturated and the excess water runs off the surface. So, that in general is the water cycle. You have evaporation, it condenses into clouds and it precipitates back and it keeps going on. But of course, there are other actors at play, such as plants. Plants, they take up water from the soil moisture and the groundwater to produce biomass. And during this process, a lot of water is also released by plants to the atmosphere through the process of transpiration. There are other processes as well, such as deposition. that means that water vapor is directly converted into ice form, and sublimation, where ice is directly converted into water vapor. But in essence, we can see that this hydrological cycle is a cyclic movement of water from one phase to another, covering land, ocean, and the atmosphere. And most importantly, these hydrological processes like evaporation, condensation, and runoff, precipitation, these processes transforms the space and time distribution of water throughout the hydrological cycle. So let's take a closer look at Earth's global water resources. So scientists have estimated the total amount of water on Earth and the different parts of the hydrological cycle. But the exact amounts are still not known precisely. So in this table, the estimated world water quantities are given, and what it says that the total water budget estimate is about 1,386 million cubic kilometers of water. So about 96.5% of all the Earth's water is in the oceans. So to give you some perspective, if the Earth were a perfectly uniform sphere, this amount of water could cover the entire surface to a depth of about 2.6 kilometers. But for life to survive, we rely on fresh water, which is about 2.5% of the total water on Earth. So, of all the fresh water on Earth, two-thirds of the fresh water is locked up in ice caps and glaciers, and most of the remainder is groundwater going to a depth of 200 to 600 meters because groundwater is saline below this depth, and only a little more than 1.2% of all fresh water is surface fresh water. So most of this water is locked up in ice, and another 20.9% is locked up in lakes. And most interestingly, rivers, like they make up just 0.49% of surface fresh water. Like although they account for only a small amount of fresh water, this is where humans get a large portion of their water from. So these points highlight how scarce and precious freshwater is, especially the small amounts we have access to. Also, this slide shows that the hydrological cycle contains different storage components, such as oceans, groundwater, soil moisture, and which are driven by the hydrological processes, precipitation, evaporation, and etc. Water balance is the most basic equation in hydrology. It's based on law of conservation of mass. It shows that if there is an imbalance between inflow and outflow, then there should be an increase or decrease in storage over time. Or we can also say that the time derivative of the storage is the difference between the inflow and the outflow, which is the water balance equation. Now let's look at the example below. If the initial storage is 10 liters, the inflow rate is 7 liters per second, outflow rate is 3 liters per second, then what will be the total storage after 10 seconds? So we can use this water balance equation to find out that. So here in the first step, this is the change in storage is equal to inflow minus outflow into time passed. So after 10 seconds, the storage had increased to 50 liters in the example. So on the graph to the right here, we visualize this inflow, outflow, and storage over time. So the inflow is in blue color, outflow is in red color, and the storage is in the green color. We can also see that like at the 10th second, the storage is 50 here. So this graph also shows that when the inflow is greater than outflow, then the storage is increasing. But when the outflow is greater than inflow, then the storage is decreasing. This is essentially the behavior of time derivative of the storage. So as you can see here, if the time derivative of storage is greater than zero, that means inflow is greater than outflow and the storage increases. And if the time derivative of storage is less than zero, then the inflow is less than outflow and the storage decreases. You can see in this visualization that for the first part, we have a positive slope, ds by dt. And for the second part, we have a decreasing trend, which is a negative slope. So this equation and the visualization, it shows how inflows and outflows, they impact storage in different systems over time. So in hydrology, the inflow can be precipitation on a surface or inflow of water, and outflow can be river discharge or evaporation from the surface. So an interesting property of such water balance system is that if we divide the storage by the outflow, we obtain a number with a time dimension. So this number represents the average time taken for a water molecule to pass through a storage subsystem of a hydrological cycle. So we can say the average residence time is storage divided by the outflow, which is also the time scale of the process. So given this problem, estimate the residence time of global atmospheric moisture. So here we can see in terms of the global atmospheric moisture, our storage will be global atmospheric moisture, which is 12,900 cubic kilometers of water. And the inflow would be the evaporation, and the outflow will be the precipitation, which is 577,000 cubic kilometers per year. So if we apply the this formula of residence time, then we get that the residence time for the atmospheric moisture will be 8.2 days. So this very short residence time for the moisture in the atmosphere is also one of the reasons that we cannot forecast weather very accurately a few days ahead. And like if you can see that the atmosphere, the water residence time is just 8 days, but when trapped in glaciers, this same water can remain there for thousands of years. So similarly, these residence time or can be also calculated for the other components of the hydrological cycle. Although global hydrology is extremely relevant for the analysis of human impacts on the planet, the natural limits of hydrological systems are much smaller. So, the natural boundary of a hydrological system is the drainage basin, commonly referred to as a watershed, a catchment, or a river basin. So, watershed being the smallest and the river basin being the largest here. So, think of drainage basin as a funnel where all precipitation collects and within the area and drains into a common outlet. So the outlet can be a river, can be a lake, can be an ocean. So a catchment area is always defined as a particular point on a specific stream. So let us see the water balance equation for a drainage basin. So it's the same that time derivative of storage is equal to inflow minus outflow. So if we consider the water balance equation for a long term, we can assume that the change in storage is negligible or zero over time. So this ds by dt, this term would be equals to zero. So what would be our inflows? The inflow would be the precipitation falling on the river basin. And what would be our outflows? The outflows would be evaporation, which is going back to the atmosphere, and the discharge, which is flowing through in the river streams. So, like the equation solves to the annual precipitation would be equal to the average annual evaporation plus average annual discharge. So, like here we can see, we'll be discussing different budgets of some of the major river basins of the world. So, as we discussed before, that like this evaporation component, it will be always greater than the precipitation, and like the proportion of runoff to rainfall, that also varies a lot between rivers, which is the runoff ratio. These are the three river basins: Nile in Africa, Orinoco in South America, Lena in Russia, that we are going to discuss here. So, as we can see, that Orinoco, it has the highest precipitation, that is about 1300 mm, and on the other hand, Nile, it has a precipitation of 220 mm per year. So the Nile River, it runs through arid and semi-arid regions where like evaporation is much higher than precipitation, which results in its low runoff. So for Nile, it is only about 14%. But in more humid climates, such as the Orinoco River, it flows through tropical rainforest where like high rainfall, as you can see, high rainfall, it exceeds evaporation, leading to high runoff ratios. That is like 70% of the like precipitation goes to the runoff in Orinoco River. But like very interestingly, there is another catchment that is in cold Siberia, and which also has the same runoff ratio. But due to insufficient solar energy, which so that it cannot evaporate most of its precipitation. So, like we can see that the different regions and different landscape, they behave very differently in terms of hydrology all over the world. And hydrology is the science that wants to describe and understand these different behaviors. So let's summarize the key concept that we have covered today. First, we talked about the hydrological cycle, which is the continuous process of water movement through evaporation, condensation, precipitation, and runoff. Next, we discussed global water resources, which showed that most of the Earth's water is saline and only a small fraction is available as fresh water. We then covered the water balance equation, which balances inflows such as precipitation and outflows such as evapotranspirations, runoff, and storage in a system. Then, lastly, we explored drainage basins, which are like natural boundaries of hydrological systems. So that brings to the end of this lecture. These are my references, and thank you for watching.